you get some number theta, how could you rewrite that as an equation involving a trig function instead of an inverse trig function? Yeah?
Just be the sine of theta.
With one more constraint, what is the range of inverse sine? Negative pi over 2 to pi over 2. So now let's reveal why I wrote a y there. Sine of theta, is that supposed to be like the x value or the y value? Y. So you should think of inverse sine as asking this question. Let's suppose you have a unit circle, and I tell you a y value that I would like you to achieve. Then this angle theta is the inverse sine of y. Maybe I should be doing that on paper. So if you want to compute arc sine of y, what are you doing? You're starting with the y coordinate you would like to see and determining which angle of rotation between negative pi over 2 and pi over 2 produces it. That is to say, you draw an angle, you draw a unit circle. If you start with some y value, maybe this one will be negative, then you want to know what angle between negative pi over 2 and pi over 2 produces it. So is that the angle that will produce the thing in quadrant 3 or in quadrant 4? Quadrant 4, yeah. So this angle is arc sine of y. We can do something similar to understand what inverse cosine means. To compute inverse cosine, what are you doing? You're fixing an x value, namely that x value. And then you want to find a theta value, an angle, theta, with cosine theta equal to that x value. So pictorially, with, well, one other restriction. Theta had better be in a particular range. What's the range of inverse cosine?
0 to pi.
0 to pi. So this angle theta had better be in 0 to pi. And we can draw a picture of that too. So I'll draw a unit circle. I'll fix some x value. Let's fix that x value. It looks like there are two different points on the circle that have that x value. Is inverse cosine going to give me the one of those that looks like it's in quadrant 1 or the one in quadrant 4? Quadrant 1, because 0 to pi is quadrant 1 and quadrant 2. So it'll give me the one that's in quadrant 1 or quadrant 2. Well, it's not in quadrant 2 because x is positive in that particular picture. So this angle is inverse cosine of x. Everyone feel pretty okay? Make sense so far? Nice. So let's just redraw that for emphasis. So the range of inverse sine is just angles between negative pi over 2 and pi over 2. That is things in quadrant 4 or quadrant 1. The range of inverse cosine are angles between 0 and pi. That is to say, angles in quadrant 1 or quadrant 2. Yes? Oh, does anyone not have the notes that we started going through yesterday? Okay. Yeah. There, and one more back. Anyone else? Cool. So, let's parse that out a little bit more. So that means that inverse sine of theta means that theta is the angle which happens to lie in quadrant 1 or quadrant 4, which satisfies that sine of theta is equal to y. Inverse cosine of x is equal to theta means theta is the angle in quadrant 1 or quadrant 2 that satisfies cosine theta is equal to x. That's the mindset that we'll have when we want to compute these compositions of inverse trig function evaluated at a trig function. So now let's go back to that problem. Let's try to think about how you can actually compute inverse sine of the sine of some angle. And maybe I should say this. So you think of like sine or cosine as being something which takes an angle and produces like a coordinate. So that means an inverse trig function you should think of as taking some coordinate information and producing an angle. So I'll try to say, well, an inverse trig function, the output, I'll try to use Greek letters because that's what I've been using for angles mostly. But let's try to do that. So here's kind of a guideline. So you want to compute inverse sine of the sine of alpha. So the first thing that I would want to do is even just think about which quadrant this angle is going to live in. Maybe even in this step, throw out any excess 2 pi's, right? If you have like 100 pi over 30, you have a bunch of extra 2 pi's that you can throw out. You can figure out how many by doing some division. If your angle is not in a quadrant that it should be, which in the case of inverse sine is quadrant 2 or 3, then, well, if you want to get from quadrant 2 or quadrant 3 to quadrant 1 or quadrant 4, reflect over the y-axis, I guess. So do that. Finally, your final answer had better be a number that's between negative pi over 2 and pi over 2, so just make sure it is by adding or subtracting some 2 pi's as needed. That makes sense? Let's try to follow these instructions then. Let's try to compute the inverse sine of the sine of 71 pi. Yeah?
I just noticed right away when we're going to do this, we have a difference, so we have 71 pi over 7.
I do actually want to do 71 pi over 7. Well, the difference between one example I do won't make a huge difference, but let's do it. Let's do the one that's actually types up there. So first things first, it says to throw out any extra 2 pi's. And so in order to do that, let's express that quantity as like a whole number of pi's plus a remainder by doing long division, I guess. That's an easy long division to do. What is 71 divided by 7? 10 with a remainder of 1. So you could re-express that as 10 pi plus pi over 7, and I think I would even, so this 10 pi, is that going to make any contribution to trig function information? Yeah, so we can throw that out. It's a different number, but if we want to draw a picture, that's what we want to do. So now let's draw a picture. So there's an angle of pi over 7. Tell me, is that angle in one of the, well, that's the question that's actually stated. Is that in one of the forbidden quadrants for inverse sine? No, it's fine, so we'll leave it alone. Pi over 7, is that between negative pi over 2 and pi over 2? Yes. So the inverse sine of the sine of 71 pi over 7 is pi over 7. What do you think we could do to check that? Sure. There's one of 2 good options. So let's do that. Let's compute the arc sine of the sine of 71 times pi divided by 7. And I'm doing, I've used a machine that refuses to do abstract computation. So it says that that's around 1.34 radians. So just remember that number, and then let's also just compute. We say that that should be the same as pi over 7. So let's also compute pi over 7. Is that about the same number? Or is it totally different? Really?
You typed in 17 pi instead of 70.
There we go. So there's the shortcoming in trusting, like, plugging into a computer to check your answer. You still need to check, did you actually plug it into the computer correctly, which apparently I can't do. Nice. So I guess here's another thing that we could do to do a quick sanity check. If this is correct, that should mean, so here's, if you like, the y value that is inside of inverse sine. So tell me, is the sine of pi over 7 the same as the sine of 71 pi over 7? I see some people nodding. Why? Why should those two be the same?
It's just the same thing with a bigger, like they have the same reference angle.
Yeah, they have the same reference angle. Those two angles differ by a bunch of extra 2 pi's, which don't change sign. Is pi over 7 in the right range to be inverse sine? Yeah, so it satisfies all of the conditions. Let's do it again, and then we'll do the same thing for cosine. Let's try to compute the inverse sine of the sine of 33, negative 33 pi over 7. And we'll play the same game. We'll re-express everything so that we can convert some extra 2 pi's. Then we'll draw a picture. So, I guess to do that, maybe there's some actual long division that needs to be done, unless you're good enough with your multiples of 7 to know that, I guess, 28 should be the multiple of 7 that's close to it. But let's suppose you don't. Let's try to see how many times 7 goes into 33. Then I'll remember there's a negative sign. So let's see, that's 4. 7 times 4 is 28, with a remainder of 5. So I would rewrite that, I think, as negative 4 pi minus an extra 5 pi over 7. Does that negative 4 pi change tree functions whatsoever? Oh, do you think, I want to point one thing out, and that's a defect in my choice of examples. You'll notice that like both of these numbers were even, and it was really important that they were. Can I throw out an odd multiple of pi? No, that makes a difference. I can only throw out even multiples of pi. So if that had happened to be 5 pi, you can only throw out 4 of those pi's. Of course, when we draw a picture, was there a question?
No, just
Okay. So let's draw a picture of this. So I want to draw an angle of negative 5 pi over 7. So let's see. Negative 5 over 7, that's more negative than negative a half, but not quite so negative as negative 1. So what quadrant will that wind up living in? 3. Quadrant 3. I'll rotate back till I get to 5 pi over 7. Is that in one of the acceptable quadrants? So, what do I need to do?
reflect it.
Reflect it over the what? No, I want to reflect it over the y-axis. I want to do the reflection which preserves y values. So that means that this is the angle that I really want to study. So this one I went back negative 5 pi over 7. And there are 2 different ways to think about this, depending on how algebraic you want to be. So if this angle is 5 pi over 7, how can we figure out what that little angle is? Or alternately, just what is that little angle?
Should be -2 pi over 7.
Maybe 2 pi over 7. Why?
Because we were that far away from reaching negative pi.
So there's one way to think of it. this angle, this is the geometric way of thinking about it, this angle that we want to know is negative 2 pi over 7. That's because this angle was 2 pi over 7 on that side. Here's another way to figure it out. What operation reflects over the y-axis? That's the operation of replacing theta by pi minus theta. So this is the pictorial way of doing it. The algebraic way is, well, that means I want to replace negative 5 pi over 7 by pi minus negative 5 pi over 7. And what happens when you go and compute that? What do you get? Yeah. Mm-hmm. Oh, yeah, okay. So these produce two different answers, so I'll try to trace through both ways into step 3. So 12 pi over 7 and negative 2 pi over 7. Both of those correspond to the same picture, so both of those will now live in quadrant 4, which is acceptable. Is this between negative pi over 2 and pi over 2? No, so that's bad. Is this between negative pi over 2 and pi over 2? So if you follow this course, you have an angle that you're already happy with. Let's convince ourselves that that's the same angle. What should I do to that to get it into an acceptable range? So at this stage, all I can do is add or subtract 2 pi's. Let's subtract 2 pi from it and see what we get. So let's see, 12 pi over 7 minus 2 pi. Let's see, that 2 pi is secretly 14 pi over 7. So yeah, that is now a negative 2 pi over 7. And I conclude that the inverse sine of the sine of negative 33 pi over 7 is negative 2 pi over 7. People feel okay about that? So here's the game. If you want to compute the sine, the inverse sine of the sine of an angle, what should you do? You start by just thinking about the angle you're given. Is that an acceptable angle already? If so, great. If not, then first, is it in the right quadrant? If not, then do a reflection to put it into an acceptable quadrant. Then think about the number you wind up with. The number that you have that corresponds to this angle you've computed might be off by some extra 2 pi's. If it is, throw out those extra 2 pi's till you're in the right range. Any questions? Think we could do something similar for cosine? It won't be literally the same, but it will be almost the same, because what are the acceptable quadrants for inverse cosine? 1 and 2. So let's use that idea. If you want to compute the inverse cosine of the cosine of some number alpha, first decide what quadrant your angle is in. And in that step, you may as well, I guess this should be capitalized, throw out any extra 2 pi's. If your angle is in a quadrant that's forbidden for inverse cosine, in this case I guess that's 3 or 4 are forbidden, then you should reflect over the x-axis.
Will you adjust the sheet?
Yes. So far the only important typo that I've fixed is the fact that y-axis should say x-axis, because that's what you actually want to reflect over. And finally, take that angle you have, express it as a number between 0 and pi, because that's what the output of an inverse cosine should be. So let's play that game. And in fact, maybe I'll let you guys, how many people want to talk through an example before I let you guys do an example? Okay. Then I'll talk through everything for 71 pi over 7, and then I'll let you guys walk for negative 34 pi over 7. So 71 pi over 7, we actually just did that one, didn't we? For sine instead of cosine, but that's okay. 71 pi over 7 how can you write that as a multiple of 2 pi plus or remainder? 10 pi plus some extra pi over 7. And the 10 pi's, if you like, we can just throw out. So we should think of a reference angle of pi over 7. Draw a picture. There's a picture of an angle of pi over 7. Is that in an acceptable quadrant?
Mm-hmm.
That's good. So that means that somehow that angle is the angle we want. We might just be off by some 2 pi's. Is that number between 0 and pi? Yeah. So it is already, so we don't have to do anything more. So tell me, what is the inverse cosine of the cosine of 71 pi over 7? Pi over 7. So in this case, all we needed to do was to throw out the extra 2 pi's and have it. Next, let's do negative 34 pi over 7. Yeah, that'll be good. Let's play the same. Let's do the same thing. So I guess first, do some division to figure out what our reference angle to study should be. So let's see. 34. I want to know how many times 7 goes into it. I guess the closest multiple of 7 is 28. That's 4 minus 28. Difference of 6, that's 4 with a remainder of 6. So negative 34 pi over 7. Looks like it's the same thing as negative 4 pi minus 6 pi over 7. Does that negative 4 pi make any difference to trig functions? No, so we can throw that out. Now let's draw an angle of negative 6 pi over 7. So let's see, that means I should start rotating down by an angle of 6 pi over 7. What quadrant will that put me in?
3?
Quadrant 3, yeah. Because 6 pi over 7, well, let's say it's bigger than pi over 2. So I'll go past the vertical line, but I don't go all the way to pi, so I don't get back to horizontal. So there's an angle of negative 6 pi over 7. Is that in an acceptable quadrant?
Mm-mm.
No. So what should I do?
Flip the axis.
I should do a vertical flip, a flip that preserves the x values. So I'll do that. And it looks like now I want to know what is this angle. And what is that angle?
6 pi over 7.
6 pi over 7. Okay. 6 pi over 7. Is that, well, let's ask first, is that angle between 0 and pi? Yeah, because 0 is 0 pi over 7, pi is 7 pi over 7. That's between them. So it looks like the inverse, the arc cosine of the cosine of negative 34 pi over 7 is 6 pi over 7. People feel okay about that? Any questions about this sort of computation? So I know there are a lot of people who are super proactive about doing their homework as soon as it's assigned. So those of you who did that, you noticed some problems in the homework that were maybe similar sounding to that. I hope those go okay. And those of you who thought they didn't go okay, hopefully they seem a little bit more practical now. Nice. So let's start in on what I want to do today. And in practice, this set of notes is supposed to be like a one-day lecture note, but as I have slightly less than half a day remaining, I won't get finished this one today. So we'll continue pushing back by a little. So there's one last inverse trig function that I want to think about. Really, there are like all four inverse trig functions you could think about. If you could talk about inverse sine and inverse cosine, then obviously you should also be able to talk about an inverse to tangent, cotangent, secant, and cosecant. In practice, though, I'll settle for just getting inverse tangent. That'll make me happy enough. And to do that, let's start the same way as we did sine and cosine. What does the graph of tangent look like? I guess I should start with this. What's tangent of 0? 0. And then there are like some vertical asymptotes. As you start going to the right from 0, what's the first vertical asymptote you see? Pi over 2. And is the y value going to be going to plus infinity or minus infinity? Plus. So it'll go up. And I guess it comes back in that way. And where is that next x-intercept? At pi. And then it just repeats. So, the standard questions. Is this function one-to-one? Nope. So, is there an inverse function to that function? No, it's not one-to-one. If you just straight up take that function and just like flip all the xy values over on the line y equals x, you will violate the vertical line test infinitely many times. But we already know a solution. What did we do for sine and cosine so that we could involve them? We restricted the domain. So let's highlight a single piece of the graph starting at 0. Let's go as far to the left and the right as we can go without something bad happening. How far to the right can we go before something bad happens? Pi over 2. And then we get to a vertical asymptote, so we'll try to just avoid that. How far to the left can we go without something bad happening? Negative pi over 2. So let's restrict to just that green portion of the graph. Oh, sorry, I didn't adjust this. Suppose better late than never, I guess. You guys aren't in section 002, you're in section 001. Not that that number affects you, but that would confuse me. Nice. So inverse tangent is the inverse to that green function. So restrict the domain of tangent to be just 0 to pi. Inclusive or exclusive? Exclusive. Oh, sorry. Negative pi over 2 to pi over 2. But yes, exclusive. So I'll take the graph of tangent and restrict its domain to negative pi over 2 to pi over 2. That now gives me a one-to-one function. Invert that function. So let's start by sketching a graph. How do you get the graph of an inverse function given the graph of the original function? Yeah, flip the x and y as you reflect over the line y equals x, whichever one of those descriptions you like best. So let's do that. So I see here that this goes to the point 0, 0. So what point will be on the graph of inverse tangent? 0, 0. Good. I see a vertical asymptote here at pi over 2. So will inverse tangent have a horizontal asymptote? What will be the y value of that horizontal asymptote? Pi over 2. So there will be this horizontal asymptote at y equals pi over 2. It'll come up to reach it. And it looks like there's also this vertical asymptote at negative pi over 2. So inverse tangent will also have a vertical asymptote at y equals negative pi over 2. Feel pretty okay? So let's ask just some basic questions by looking at that graph. So there's the graph of inverse tangent of x. What's the domain of inverse tangent?
Negative infinity to infinity.
Negative infinity to infinity, all the way along You can plug anything into inverse tangent. What is the range of inverse tangent? Negative pi over 2 to pi over 2, inclusive or exclusive? Right, because that range should be the same as the domain of the function that we inverted. And we restricted the domain to negative pi over 2 to pi over 2, so these two had better be the same. Now let's just recall some things. So I just want everything written in the same place. What's the range of inverse sine?
Negative 1 to 1, inclusive.
Are you sure you mean that? I think that's the domain.
Oh, yeah.
Which may be like you're reading from the previous notes, and I think I had domain and range in the opposite order. What's the range of inverse sine? Negative pi over 2 to pi over 2. Inclusive or exclusive? Inclusive. So that's a difference between inverse sine and inverse tangent. The domain of inverse sine includes its endpoints. And that makes sense, right? You can't plug pi over 2 into tangent. So that better not be an output of inverse tangent. But you can plug pi over 2 into sine. Inverse cosine. The range of inverse cosine is 0 to pi. What is its domain? Negative 1 to 1. Inverse tangent has a range. Oh, and that's exclusive. And what is its domain? All real numbers. Pick your favorite way of indicating that. And now let's remember some more things from last time. So what we just busied ourselves doing was computing the inverse sine of the sine of theta, and that got complicated. What about the sine of the inverse sine of x? Was that complicated? That was always equal to x, as long as you're in the appropriate domain. What's the domain of inverse sine of x? What about the cosine of the inverse cosine of x? Was that always equal to x?
Yep.
As long as you're in the right domain. Oh, sorry. So there's a mathematical shorthand that so far I think I've avoided this class. Frequently enough, you want to say that a thing is in some set, that there's a mathematical shorthand for that, and that's what I had put there. I think that's the first time I've accidentally dropped that symbol in this class. But that's what I meant. What about the tangent of the inverse tangent? What should that be? X. That should also always be x, because, right, inverse tangent of x, that should be saying, okay, what theta results in the tangent of this x? And if you start with a theta that has tangent equal to x and evaluate its tangent, you'll get x. And that sounded like a lot of words that were talking in a circle. And that's exactly why it's x. Nice. So I can evaluate sine of the inverse sine of x, cosine of the inverse cosine of x, tangent of the inverse tangent of x. But what if I start mixing them? What if I try to compute the sine of the inverse cosine of x? What should that be? The cosine of the inverse sine of x. So anything that looks like a trig function evaluated at an inverse trig function. Let's try to figure out what those will be. And what my goal in this document will be, mainly, will be getting these two formulas. And then later on, I'll get a formula for one of them where like one of these inverse cosines is an inverse tangent. That's what the goal in this document is. And if you read the corresponding section in the book, you will find that the book will happily provide you with all 6 of the relevant formulas that you could possibly want by doing this. But I want to actually, I don't care about, I mean, I do care about what the formula is, but I care more about where the formula comes from. So let's figure out where the formula comes from by just doing a computation first. So let's try to evaluate the cosine of the inverse cosine of 3 over 5 and figure out what that is. Where that number 3 over 5 is chosen so that the resulting computation will have fewer ugly numbers that show up midway through it. The ugly numbers won't actually be bad. So let's try to do it. So let's see. So this means that I should think of this as like an angle, right? There's some angle theta. So you should think of inverse sine as being an angle. It's an angle whose sine is 3/5. So just in order to give it a name, let's call inverse sine of 3/5 theta. If theta is the inverse sine of 3/5, then tell me, what is the sine of theta? 3/5. Yeah. Oh, wait. So that means that, what is this question saying? This question is asking you to compute cosine of theta, given that you know what the sine of theta is. Have we done that in the past a bunch of times?
Yeah.
Yeah. So let's do that. Maybe we'll start with quadrants. So let's draw a picture. So inverse sine of 3/5. That's allowed to be in quadrant 1 or quadrant 4, right? Those are the two allowed quadrants for inverse sine. So let's see, the range of inverse sine is equal to quadrant 1 or quadrant 4. But I know that the sine of this angle theta is 3/5. So which quadrant do I actually land in?
First one.
2.
First one.
It's quadrant 1 or quadrant 4, right? It's quadrant 1 then. Yeah, the range of cosine was quadrant 1 or quadrant 2. All right, so I know that this angle theta has to be somewhere in that green range. But I know that the sine is 3/5, which is about there. So in fact, this lands in quadrant 1. Since it's in quadrant 1, is cosine positive or negative? Positive. In fact, if it were in quadrant 4, would cosine be positive or negative? Positive. So I know it's in quadrant 1, but even if I couldn't figure out that it was in quadrant 1, if I knew it was in Q1 or Q4, we would get the same information. Cosine is positive. So that means cosine of theta will be positive, which it's shorter to write bigger than 0 than positive, so it is bigger than 0. Is that enough information to figure out what the cosine of theta is? Yeah, and I'll do it 2 different ways. I'll do it algebraically, and then I'll use a right triangle to do it. And I think that'll eat up all my time. So first, let's do it algebraically. Let's solve that for the cosine of theta. And maybe in order to shorten things, I'll set c equal to the cosine of theta, so I don't have to write cosine of theta so many times. So let's solve c squared plus, what's the sine of theta? 3/5 squared is equal to 1. Let's solve that for c. So I guess that'll give me c squared is equal to, oh goodness, 3/5 is 9 over 25? So I'll subtract that to the other side. I'll replace that 1 by 25. over 25 minus 9 over 25. What's 25 minus 9? 16 over 25. Is that a perfect square? Nice. That makes it easy to take a square root. So that means C is positive or negative 4/5. So cosine of theta is plus or minus 4/5. Is it plus or is it minus? Plus. So that means that cosine of this angle, which is the cosine of the inverse sine of 3/5, is 4/5. Cool. So that's like the algebraic way of doing things, but we can also do this in a more geometric way. I know that this angle theta has a sine of 3/5. Let's encode that in a right triangle. There's a right triangle. So katoa, what numbers can I put in that triangle? I may as well set that to be 3 and that to be 5. Or it could be 6 and 10, or 1 and 5 thirds, anything that has the right ratio. Is that enough information to figure out the adjacent side? What's the adjacent side?
4.
Yeah, and in order to do that, you would have to do like the same amount of work as you did up here, but at this point, you've memorized that 3, 4, 5 is a Pythagorean triple. So, using this picture, what's the cosine of theta? Cool. I'll give you this caution. If I asked you to compute the cosine of the inverse sine of 3/5, it might get just a teensy bit more confusing. You still could. You just have to think about what that negative sign would be. Cool. So we'll pick up on this next time, and we'll start by doing this. We'll do the exact same thing, but for an arbitrary x value instead of 3/5. Oh, thank you. And let's see, as people are packing up, I will remind you that I want to collect the review document for the midterm on Friday. And at this point, the grades to that midterm are posted. They're lower than I was expecting. So in order to account for that, I'll be more liberal with giving points back for the review document. But still, if you got a 90% or above, don't bother putting in the review document, then I'll give you points back anyway. Well, you can put it in, but I won't look at it.